What if we could keep our food and drinks perfectly chilled, with a refrigerant as natural as water, and cool our cars, homes and workplaces as efficiently as a fresh sea breeze? At Engas, our hydrocarbon refrigerants are created by nature, not a chemical company, and can save you up to 40% on your cooling and heating costs. To help create a better future for all, Engas is cooling our world naturally.
So yeah, Engas is we're based in Perth, Western Australia. We manufacture, distribute, supply blended hydrocarbon refrigerants through Australia, into Indonesia, into Malaysia, Thailand, the Philippines and China. I've been in the industry 35 years. I've been working with hydrocarbon refrigerants for the last 12 years, and our technical director is Dr. Ladis Taylor. He studied hydrocarbon refrigerants at the University of South London about 30 years ago. So what we do, although manufacture and distribution is our core business, we do provide in-house training because we feel it's necessary for the safe application and correct use of our refrigerants. By way of example, back in January this year, we trained 14 engineers in Kuala Lumpur. 3 weeks ago we were at the TAFE in South Australia. They've got a brand new natural refrigerants section there where they've got ammonia, carbon dioxide and hydrocarbon. And so we trained 20 engineers there. In 2 weeks' time I'm back in Shanghai and moving over to Suzhou, which is 2 hours west of Shanghai, and we've got 30 engineers to train there. Yeah, so I think a lot of the previous speakers have given a brief overview on natural refrigerants. We know what they are. But our focus at Engas is only on hydrocarbon refrigerants. We don't get involved in ammonia or CO2. And the reason that our refrigerants, we have blended refrigerants, we have 4, and they're designed to provide the maximum energy efficiencies we can achieve when retrofitting or when replacing the chemical refrigerants. We have a full range of refrigerants suitable for all the chemical refrigerants that are on the market, R22, 410A, 134A, 407C, the whole lot. We can do all refrigeration or air conditioning systems that have a positive displacement compressor. We cannot do centrifugal compressors at this stage. So our refrigerants, hydrocarbon refrigerants, are 50% more efficient conductors of heat than fluorocarbon refrigerants. The operating pressures on the discharge side are between 20 and 30% lower. So these operating pressures, the reduction reduces the work that the compressor has to do and reduces wear and tear. There's less pressure on the pipework, the joints, the hoses, fittings, and the likelihood of leaks. So this can and does extend the working life of the equipment. Yeah, so for those of you here that are not familiar with hydrocarbons, they're not bang gas or a cowboy gas. They're recognised by the world's leading industry bodies, and they're given R numbers such as R290, R170, R1270. Our refrigerants, we sell them. We have a range from M10 through to M60, and we do that because we sell into Asia. But each of those refrigerants, for example, M50, is a blend of R290, R170 and R1270. So we give them the M numbers for simplicity. Safety is the biggest issue with hydrocarbons, and for me, the safety with hydrocarbon refrigerants, I'm not afraid of them, I'm not scared of them, I respect them. It's just like electricity. I know what electricity can do, but I've been trained to deal with it and to apply it safely and correctly. And that's how it is with hydrocarbons. They can be applied and as safely as correctly as any other refrigerant. We have to remember that hydrocarbon refrigerants are used, or hydrocarbons, as a fuel, are used all over the world every day for cooking and for heating and powering vehicles. And as aerosol propellants for hairsprays, deodorants, whip screen and cooking sprays. They can be used safely. And then if we look at the chemical side of the industry, in refrigeration and air conditioning systems which use chemical refrigerants, oil mixes with the refrigerants and travels around the system, all these chemical refrigerants become flammable due to the oil vapour content of the gases when being discharged from the systems. Most chemical refrigerants produce toxic byproducts and poisonous gases following accidental release in the presence of an adequate heat source. So, since the 1930s, the fluorocarbon industry has been promoting their chemical refrigerants as safe and hydrocarbons and other refrigerants as dangerous. This is mainly for commercial reasons. If you've got, they talk about the heat of combustion, and with the heat of combustion, if you have the heat of combustion, you must have the products of combustion. So the products of combustion for hydrocarbon refrigerants are carbon and steam. But for chemical refrigerants, especially the latest ones introduced, the fourth generation HFCs, the products of combustion are hydrogen fluoride and carbonyl halides. And Professor Corneth from Munich University presented to the European Parliament, and he insisted that these new HFOs, they shouldn't be used because 30% of the refrigerant becomes a hydrogen fluoride when burnt or overheated. Now, the fluorocarbon industry argued with him on that, and he was talking about the refrigerant HFO 1234YF used for motor vehicles. And he said, well, the evidence is in the glass. When the car catches fire, the glass melts and the glass is etched. That didn't happen with 134A. So I don't think we've been told the truth about these new generation refrigerants coming onto the market. So the reason we can be confident when dealing and handling hydrocarbon refrigerants is because we know what they do. It's the laws of physics. We know they don't just twist and turn like a snake. So three elements need to coincide for an incident to occur. So there needs to be a release of hydrocarbons, a leak. The hydrocarbon needs to mix with the correct proportion of air, the range of flammability being between 2 and 10%. And then an ignition source exceeding 460 degrees Celsius must be present. So if one of these elements is eliminated, combustion cannot occur. It is impossible. The envelope showed there in red, it's very small. I think if you look at acetylene, the envelope is between 1 and 99%. It must remember, as I said earlier, all refrigerants burn. It's just some have a higher auto-ignition temperature than others, but there are two issues which really make this difference in auto-ignition temperatures meaningless. It's the auto-ignition temperatures. If we look at the chart there, you'll see R22 at 740 degrees Celsius, 134A for example at 647, and of course those two refrigerants are regarded as non-flammable. There's a mysterious line across 500 degrees Celsius which determines whether a refrigerant is flammable or non-flammable. So we've got R290 propane and R600A just below 500, but the main issue here is the oil. Auto-ignition temperature of oil is 262, sometimes down to 240 degrees Celsius. And when it ignites, it burns at 2000 degrees Celsius, and it takes everything else with it. So this is just a simple way of looking at it, the flammability triangle. And there we have the fuel. So if we have a leak, we have to have the right mix with oxygen, and we have to have the ignition source on the bottom. And there we are. If you take away one, it is impossible for an incident to occur. And so what we do when we're designing plant room chillers or split systems, refrigeration systems that need to be made safe, at NGAS we've developed hydrocarbon sensors, and they initially start sensing. They'll pick up a hydrocarbon leak at 2,000 parts per million, and they have auxiliary contacts. So as soon as the leak activates to about 4,500 parts per million, which is 0.05% of LFL, the hydrocarbon sensor will activate, and by that we can start up extract fans, we can close liquid line solenoids, we can pump the system down, we can bring on our red lights, we can send messages to building management systems, and we've been using those sensors for the last 4 or 5 years. If we just summarise the flammability and also toxicity does not give a clear judgment on which substance is lethal. For example, ammonia is classified as a toxic refrigerant. However, its distinctive smell will give an early warning so that it will not be lethal. Although R22 is considered a safe refrigerant, many have been suffocated from it due to its lack of odour or smell. I know of a refrigeration engineer in Perth. He's in his mid-60s now, but he lost his son at the age of 21 in a fishing boat down at Fremantle Harbour. He was asphyxiated from R22, and yet we consider R22 to be a safe refrigerant. I think it's important, I think it was said earlier, but all refrigerants are dangerous, and in fact all compressed gases are dangerous, so they should only be handled by trained personnel. And then if we just go back to hydrocarbons have been used in plant rooms for fuels for over a century, and there are acceptable standards for the use in large quantities. So consequently, if boilers can be safely installed in plant rooms, the use of hydrocarbon refrigerants for large chillers in plant rooms should be even safer. We don't deliberately ignite the refrigerant in a boiler. We're getting on to the energy efficiency now, performance characteristics. People often wonder why hydrocarbon refrigerants are so efficient. We quite often get told that no, that can't be right. But the reason is that the molecule size of a hydrocarbon refrigerant is less than 50% that of a chemical refrigerant. And so when we measure that in kilojoules per kilogram, we get quite incredible results. On that slide you'll see 410A with a refrigerating effect of 217 kilojoules per kilogram, whereas our N-gas M60, the kilojoules is 435 per kg. So what we get when we replace a 410A system with our M60, we get traditionally a 35% reduction in amps immediately with no loss of capacity. With our M50, which replaces R22, we normally get an average 22 to 25%. We've just designed a new refrigerant to replace R32, and we get over 50% reduction in amps. That's just a general information table. There's a lot in there, but I think that's on our website if you want to have a look. And so now I'm just going to go to some case studies, and if we can start with Adelaide Terrace, please. So this building, we did, Dr. Taylor and I did this in 2008. It's been running 8 years. It's in the Perth CBD. The chiller is used for air conditioning, for chilled water. It's a Carrier 30 HXC 230, so it's 230 tonne or about 820 kilowatts of cooling. It was on refrigerant 134A, and we converted it to our M30. We data logged it before and after, and at the point of conversion we estimated a saving of 25%, but the building owner claims that they've achieved a 30% reduction in their electricity bill. This chiller has been inspected by the fire department and WorkSafe, and as of most of our installations in Perth and even over here in New South Wales. You'll see the charts which were created from the raw data that we collected from the data logger, and the savings is quite impressive, and every time we do a chiller we get in the vicinity of 25%. The next one is maybe Citibank House. So we did a project about 3 years ago in Perth. It was for Citibank House on St George's Terrace, and it's a chiller, is a 814 kilowatt Carrier, two circuits, 8 compressors, 4 on each side, semi-hermetic. The chiller's about 20 years old and was running on R22. There we are. And so we converted to our M50. Before we did that, we had to make it safe. And so what we did with the plant room, we put a wall down the centre of the plant room, and we isolated the main switchboard and the pumps to one side. On the chiller side, we put in the large extract fan you can see on the floor. The extract fan is designed to remove the entire cubic volume of air in the room within 30 seconds. There's 4 sensors on the floor, about 300 millimetres off the floor, because hydrocarbon's heavier than air, and each of those sensors will start the fan, but they'll also cut the power to the room apart from the lighting. So alongside that, there's also 2 electrical kill switches on the wall for servicemen. So if they're in there and something goes wrong, they can just hit the kill switch. So there's no ignition source. It's not possible for the vapour, for the refrigerant escaping if there's a leak. Even if it was a discharge line, it's not possible for that to raise to the 2% dangerous level, because the fan will take care of that. Also with these plant rooms, we always pipe the pressure vessel safety discs, relief discs. We always pipe them to the outside of the building. Now with Citibank House, that was never done, even though all manufacturers recommend it, even for R22 or other chemical refrigerants. And several months prior to us doing this conversion, one of those discs erupted and it dropped 75 kgs of R22 into the car park of the building. So most of these case studies are on our website. In January last year I travelled to China and we got a distributor in Shanghai, and we did a project for Bosch and Siemens home appliances. They're up in Suzhou, which is 600 km northwest of Shanghai, and we converted a chiller for them. It was 1049 kilowatts. It's a Clima Veneta out of Italy, 2 compressors, two twin screw compressors. It was on 407C, and we got our Chinese partners to build a room and to put in the ventilation and the sensors, and we achieved a 28% saving on that. So for the chiller was drawing 563 amps per phase, and we reduced that by 28%. They used the chiller for plastic injection molding, for process cooling, chilling water to cool the machines. And the machine runs 7 days, 24 hours, and it runs for all year except for Chinese New Year. And so the savings is about 150,000 US per annum, just on electricity. I'll just go through one. This is a lead food company in Malaga industrial area in Perth, and he's a food wholesaler, and just a large cool room and freezer room, and running on N-gas M50. The plant room is at the back of the building, and there's a fan on the floor again, extract fan 500mm 3-phase, and N-gas sensors in the room, so it automatically starts up if there's a leak. The sensors inside the freezer room and cool room will close the liquid line solenoid, and the system will pump down if there's ever a leak inside. So I think it's fairly clear that all existing fluorocarbon refrigerants are going to be phased down, and they're going to be phased down fairly quickly. I think even the European Union, although the phase down is 79% by 2030, I think it's going to be forbidden to sell new equipment using an HSC from about 2023. I'll just summarise, there are many benefits that do arise from converting old refrigeration air conditioning equipment to operate on hydrocarbon refrigerants. So these include savings on both capital and operating costs, and I'm hoping that I've convinced everybody here today that hydrocarbon refrigerants can be applied correctly and safely, just like any other refrigerant. So by choosing natural refrigerants over chemical refrigerants, you can gain an immediate financial benefit. You'll also help our children and grandchildren to have a brighter future, and you'll contribute to the welfare of many future generations. Thank you.